Yeah, thumbs up. We're working. All right, so yesterday we were looking at the introduction to Taylor polynomials, and we did it by way of a tangent line. So a tangent line is a first-degree Taylor polynomial. And what that means then is in the neighborhood of the point of tangency, which we looked at sine of x at 0, the tangent line becomes a pretty good approximation for the sine values in the neighborhood of 0. And there's a comfortable radius that we can kind of travel left and right from the point of tangency to get decent values. But notice I would not use the line to approximate sine of, let's say, 2 pi. Because sine of 2 pi I can see is 0, and the line would be way up there at y equals 2 pi. So left and right by a comfortable margin. That's called tangent line approximation, but that's also Taylor polynomial approximation. So what we were doing at the end of class yesterday was I was typing in terms into the calculator to show you that, hey, maybe if a first-degree Taylor polynomial, that's line, is a good approximation, maybe there is a quadratic or a cubic or a quartic that would do a better job. And the answer is yes, there are. But because sine is a function that is what? Even or odd? Sine? Sine is odd. It has origin symmetry. If I'm going to be representing sine then by a polynomial, the polynomial also has to be an odd polynomial, okay, with origin symmetry, which means it needs to be an odd degree. And I'll show you how to generate these terms here in a little bit. But what I've done is I've typed in sine of x in y1, and then I'm adding essentially another term to each of the previous graphs. And if you notice the terms, they're all odd degree. So I have an x to the first, then I have an x cubed over 3 factorial, an x to the fifth over 5 factorial, x to the seventh over 7 factorial, x to the ninth over 9 factorial. So you could probably predict what the next term would be if I were to add another one. X to the 11th over 11 factorial, because we're going by twos. We're counting by odds. Now, the other thing that's interesting to note is notice the terms that I keep adding alternate signs. Right? So it's minus, plus, minus, plus. That's a pattern that you're going to memorize, and I'll show you where these terms come from here shortly enough. But if I hit graph, here's what we see. There's sine of x. There's x. Here's the cubic. Here comes the quintic. Here's the 7th degree polynomial coming in. And then you'll have the 9th degree polynomial coming in. And I didn't do the 11th, but we could add the 11th. So notice, yeah, it looks pretty cool. The underarm logo? Oh, Under Armour. Okay. Does an underarm have a logo? All right. So notice that every single one of these polynomials and the graph of sine have the exact same value at 0. 0 is the point of tangency, but we don't really call it a point of tangency for things that aren't lines. So we call that the center of the approximation. 0 is the center of approximation. And the functions and those polynomials have the exact same value there. If we drift left and right, now the polynomials become just approximate values for the sine. And they are pretty dang good approximations. The higher the degree, the better the approximation, okay, when you're closer to 0. So all things being considered, the higher the degree, the better the approximation. But also notice what else is happening. As I put a polynomial of higher and higher degree, that polynomial itself is coming in a little bit sooner, and it's starting to wrap itself around the graph of sine of x over a larger interval, right? Now, in theory, I could keep adding these odd terms for how long? Forever and ever and ever. And it turns out, and this is the next section, that if you add infinitely many terms to a polynomial, it doesn't just become an approximation for sine of x, it becomes sine of x. In other words, the graph of an infinitely termed polynomial will wrap itself around the graph of sine of x entirely and exactly. But of course, what's the problem with using infinitely many terms? It's infinite, right? We can't do it. We need something finite. And so that's why we talk about the Taylor polynomials. We decide how many terms we want to use, and we come up then with a polynomial that just approximates this graph of sine of x for given values left and right of our center. Now, if I wanted to approximate something way out here, let's say at 5 pi, I probably wouldn't center my approximation at 0. I'm going to show you how to create these polynomial equations, and one of the things that we want to consider is what is a reasonable place to center our polynomial around if we want to get a good approximation. So it's kind of neat. It's like a curve wrapping function, and it wraps around beautifully. All right, let's just do one more before we get away from this. Let's type in the next term. And Megan, why don't you tell me what to type in?
It's going to be y7.
Okay, so it's what I had previously, all of them, which would be 7. And now I'm going to minus.
X to the 11.
Over
11 exclamation point.
Right. And remember how we get the exclamation point, the factorial? You found it under math. And it's under probability, so you click to the left twice or right 3 times. And there it is, number 4. So if I do that, it'll come in now with this 11th degree polynomial. Okay. Yeah, because I guess it's finite number of colors. All right, so there you go. Pretty nifty. That is the idea behind a Taylor polynomial. All right, so let's go ahead and get a, well, actually, before I do that, I'm trying to move fast, but I don't want to compromise anything. Let's go ahead and hit the trace button, and let's type in 0.2. So notice I'm on the sine function. Let's type in point. I want to get a little bit further away. How about 0.8? Sine of 0.8 is, I'm in the wrong mode. Okay, my bad. Let me go to my format, and I need to be in rectangular. All right, one more time. Let's hit trace, and we'll type in 0.8. So sine of 0.8 is 0.717. Got it? If I click down, now I'm on the x. If I type in 0.8, I'm going to get 0.8, which is about 0.7. If I click down again, now I'm on the cubic. If I type 0.8, I'm going to get 0.714, which is a little bit closer to what the actual sine value was. If I click down again, now I'm on the quintic. If I type in 0.8, I'm going to get a number that's even closer yet to what the actual sine value is. If I click down to the 7th degree polynomial and figure out what that value is at 0.8, that's a number now that's yet even closer to the actual value, and so on and so forth, okay? So it was a trade-off back in the day before the calculator. Polynomials are much easier to evaluate than sines, but typing it into the 7th power for a small decimal is still pretty tedious. So the more terms, the more accurate, but also the more tedious it was. So it's kind of a trade-off. Let me get this. This Corpy. Hi. Yes, this is a bad time. Can you call back in about 25 minutes? Okay, great. That was a student from another high school somewhere else in the United States that uses Corpy's World, and they had a math question. Oh, they can't come into tutorials for me, so they call me. That's interesting. Okay, that's never happened before, a phone call. Okay, so let's go ahead and look at this right here. The definition of an nth degree Taylor polynomial. This guy here, the Taylor polynomials we've been using all year, it's named after this guy here. And what is his name? Brooke Taylor. Could be. He's running for king, yeah. This is Brooke Taylor, and he's the guy that came up with the way to construct these polynomials that approximate these functions. So just like there's a routine way to construct the equation of a Taylor tangent line, there's a way to develop it for any polynomial. So here it is. And this is probably the most important thing that we're going to do the rest of the year, this formula, okay? If you have a function f that has n derivatives, in other words, you can take the derivative up to whatever you want n, at x equals c. We're going to use c for the center of the approximation. Then you can approximate that function f with a polynomial function of degree n as a function of x. And here's what it's going to be. It's going to be the y value at that x value plus the slope times x minus the x value. If I just stop it right there, does that look familiar to you? That's the Taylor form of a tangent line, right? It's the y value plus the slope times x minus the x value. Here's how you generate all the rest of the terms. It's now the second derivative over 2 factorial times x minus the center squared. The next term would be the third derivative at the center over 3 factorial times x minus c cubed. The next term would be the fourth derivative at the center over 4 factorial times x minus c to the fourth, so on and so forth. Here in general is what it's going to be. It's the nth derivative at the center divided by n factorial times x minus c to the nth. This little piece right here is all you have to remember. Now, when we've been doing tangent line approximation, it works the same way because this you could think of as the zeroth derivative. It's the zeroth derivative at the center divided by 0 factorial times x minus the center to the 0th power. This piece here is like the first derivative evaluated at the center over 1 factorial times x minus c to the first. Okay, now we don't really have to write that because we're so used to writing equations of tangent lines, and the pattern really picks up here on the second derivative. But why does it work? The 0th derivative is really like the function. And what is 0 factorial? 1, right? So this just becomes the function value at c divided by 1, which is f of c. And what's anything to the 0 power? 1. So this pattern simplifies down to just f of c. The next term, f prime of c, of course, is what we're used to. 1 factorial is also 1. So that becomes f prime of c, and then x minus c to the first is this. But then after that, it's the nth derivative over n factorial times x minus c to the n. Okay? Got it? That's how we generate all those terms that I was typing into the calculator. It's pretty neat. And you could do it for any function that has derivatives that exist. That's awesome. Okay? And we saw that there's still relevance today because that's how your TI calculators compute. Computer programs would rather do more calculations that are easier than fewer calculations that make the numbers bigger. So whenever they compute like an exponential number, they probably use, I'm guessing, a Taylor polynomial to compute it. It's more calculations, but the numbers stay smaller. So for programming, these are still important. Now, this guy here is not Brooke Taylor. This is Colin Maclaurin. And wigs were a big thing back there. Okay? Nice coif. He looks like a poodle, yeah. He actually came up with a Maclaurin polynomial or a Maclaurin series. And the only difference between a Taylor polynomial or series is that it's centered at a specified value c. Okay? Whereas the Maclaurin series is always centered at 0. Always centered at 0. Now, which one of these do you think came first? Maclaurin or Taylor? Maclaurin. It would be really silly if Taylor came first and Brooke said, yeah, in the special case, then when c is 0, I'm going to name it after myself. It's kind of like Rolle's theorem came before the MVT, all right? So the very specific case when you centered it at the 0, which is like we saw with sine of x, that came first, and then Brooke kind of take it to the next level, made it more general, and it allows you to shift over and center your approximation at any value of x. Okay, it says note. A first-degree Taylor polynomial is a tangent line. Okay, good. Note 2. These are the coefficients, then, of your polynomial. The nth derivative at the center divided by n factorial. Those are your coefficients of the x minus c to the nth term. There's going to be a lot of problems where we're working just with the coefficients. It's the nth derivative over n factorial. Note 3. Maclaurin not only got his name on a very specific case of Taylor's work, but he also had big hair. Note 4. For Taylor and MacDaddy series or polynomials, you must use a squiggle. Why? It's the same reason when we did linearization, because we are just approximating the function. They are only the same at the center. They're only approximated everywhere else, because these are actual polynomials, not series. And then if you want to read all this, there you go. It gives a little bio of Taylor and Maclaurin. All right, so here we go. Example 3. Find the Maclaurin polynomial. Now, when I say the word Maclaurin, you should be thinking that we're going to center our approximation where? At 0, okay? For sine of x. So I'm going to show you where those terms that we just typed in came from. So here's what you're going to want to do. You want to collect all your information first. So we're going to have f of x equals sine of x, and then you're going to evaluate it at the center 0. What is sine of 0? 0. Okay? So we're going to do this every time. We're going to have our function, the function evaluated at the center. We're going to make 2 columns. Now below there, we're going to need the first derivative. So what's the first derivative of sine? cosine. And now we're going to need to evaluate that at 0. So what's cosine of 0? 1. And now we're going to need the second derivative, which is negative sine. And now we need the second derivative at 0. I'm not going to write negative sine of 0, but what is negative sine of 0? 0. And then we need the third derivative, negative cosine. And then the third derivative evaluated at 0 is negative 1. And then the fourth derivative, remember after that we switched to Arabic, is positive sine. And then the fourth derivative at 0 is 0. And then finally, since it said a fifth degree Taylor polynomial, we'll go to the fifth derivative. And the derivative of sine is cosine. And then finally, the fifth derivative evaluated at 0 is 1. Okay, so once you have all that information, that's just going to then allow you to assemble it very quickly. So here's what we're going to do. Sine of x then can be approximated by. Now here's what I would always recommend, so you don't get caught up in the pattern, because the pattern doesn't really make itself visually obvious until the second derivative. Just set it up like you would if you were writing the equation of a tangent line, right? What do you need for the equation of a tangent line? A point and a slope. So what's the ordered pair? 0, 0. Okay, my center is C. So the y value there is 0 plus the slope at 0, which is 1 times x minus the center, which is 0 to the first. Okay? So those are going to be the first two terms in the Maclaurin series. Now, we'll go ahead and go to the next term. The coefficients, remember, are the nth derivative over n factorial. So since this is n to the first, it hasn't been 25 minutes, we're on 2. So we look at the second derivative line. So what's the second derivative at 0? 0 over 2 factorial times x minus 0 squared plus, now we're going to go to the third derivative line. What's the, it's the third derivative over 3 factorial. So the third derivative is negative 1 over 3 factorial times x minus 0 to the third. And now we go to the next line, the fourth derivative. The coefficient is going to be 0 over 4 factorial. 0 over 4 factorial times x minus the center to the fourth. And then finally, the last term, we're on the fifth derivative line. It's going to be the derivative, the fifth derivative, which is 1 over 5 factorial times x minus the center to the fifth. So notice this is just using these numbers. The coefficients are the derivative divided by n factorial times x minus the center to that number. Now, if you simplify this, great things will happen. This actually equals, of course, the first term drops away, and the next term is just x to the first, which is x. What happens to essentially all of the terms with an even exponent? They disappear because the numerator of the coefficient is 0, and that's why we only saw odd terms. So the next term after x would be this one over here, which is now minus, and it's x cubed over 3 factorial, plus 0, so that's gone. And so now the next term is plus that, which is plus, if we simplify x to the fifth, over 5 factorial.
Every time I read those, I'm like,
Yeah, you get excited, right? Yeah, I agree. I like it. So here you go. Every single function can be generated with its Taylor polynomial or Maclaurin polynomial in the same fashion. But then the pattern that emerges from Taylor's rule, as it's called, or Maclaurin's rule in this case, it generates its own inherent pattern, so that if you needed to generate more terms, you wouldn't necessarily have to generate more derivatives and use Taylor's rule to generate them, because you could see the pattern built into that specific function, right? In this case, then we would realize that the terms alternate signs, plus, minus, plus. So the next term would be, of course, what? Minus x to the 7th over 7 factorial, okay? So there's always two patterns. There's the Taylor's rule pattern, which is how you generate the Taylor polynomial for any function, and then the inherent pattern for that specific function. Okay, so this would be a fifth degree polynomial that we could then use to approximate sine. So now I could say sine of 0.1 is approximated by, and if you want to give this polynomial a name, let's call it m sub 5 of x. That's typically what we do. Why m? Because of Megan. Right, exactly. Or Maclaurin.
Or that.
Yeah? And the subscript usually tells you what degree it is. So this would be a Maclaurin polynomial of 5th degree. But you could just put f of x if you want. Okay? So it's going to be approximated by a 5th degree Maclaurin polynomial at 0.1, which now equals 0.1 minus 0.1 cubed over 3 factorial, which is really 6, but I'll leave it as 3 factorial, plus 0.1 to the 5th over 5 factorial. Now imagine if you're someone back in the day and you didn't have a calculator, finding 0.1 to the 3rd and 0.1 to the 5th would not be that bad at all. This math on the right-hand side is a lot nicer, a lot easier than trying to figure out, thank you, what sine of 0.1 is. So we have different ways now to approximate functions near a point of tangency, don't we? We had linearization, which now we know would be just the 1st degree Taylor polynomial. It would be 0.1. There was another method that we learned to get more accurate, but still using lines. What was that called? If we wanted to venture out from the point of tangency, but still use lines, Euler's method. Okay, that's another way to approximate. And now we have this other method that uses higher degree polynomials to approximate near a point of tangency or from a center. So it was a big endeavor back in the day to try and approximate functions at funky values. And using polynomials were the easiest way to do it, and using lines would be the easiest type of polynomial. All right, so you want to memorize sine. You want to memorize the pattern for sine. Sine is an odd function with origin symmetry, so it's an odd polynomial. It starts with positive x to the 1st. Signs alternate after that, and then it's just x to the exponent over the exponent factorial. Okay? Now let's do this example 4. Find the Taylor polynomial of degree 6 for the natural log of x. This time we're going to center it at 1, and then we're going to use it to approximate the natural log of 1.1. Now, if we don't finish before lunch, we'll just pick up after lunch. Now, why did I center my function at 1 instead of 0? Because 0 is the easiest place to center it. Natural log is not defined there. Very good. Okay, so we're going to need our information here. The function f of x is the natural log of x, and now I need to evaluate it at the center, which is 1. So what's the natural log of 1? 0. So you could think of this as n equals 0. The function is really the 0th derivative. Now, the first derivative, f prime, that's when n equals 1. That's 1 over x, right? So f prime of 1 is 1. The second derivative, when n equals 2, well, can you do it in your head and simplify it? It should be negative 1 over x squared. Yeah. And then the second derivative at 1 is now negative 1. The third derivative, this is really negative x to the negative second. So when you multiply, you get positive 2x to the negative third. So it's 2 over x cubed. And then the third derivative at the center is 2 over 1, which is 2. The fourth derivative, again, doing it in your head, that's really 2x to the negative third. So when you multiply, you get negative 6x to the negative fourth, which is really negative 6 over x to the positive fourth. So the fourth derivative at 1 is now negative 6. And then we got to go out one more because it did say, ooh, degree 6. So this is not a necessarily fun thing to do, but at least it's a systematic process. The next derivative would be 24 over x to the 5th. And then the fifth derivative at the center would be 24. And now we're on our last one. The sixth derivative would be negative 5 times 24, which is negative 120, all over x to the 6th. So then the sixth derivative at 1 is negative 120. All right, so here we go. Before lunch, we can sneak this in. The function f of x equals ln of x is now approximated by, and let's go ahead and always just consider the first two terms the way we've always done it for equations of a tangent line. What's the y value at 1? 0, 0, plus the slope, which is f prime of 1, which is 1 times x minus the x value, which is 1, right, to the first power. So there would be the tangent line. That would be the first degree Taylor polynomial. But now we're going to kick it into the next gear. So now we're on n equals 2. This is x to the first. So now we're on the second derivative line. The numerator of the coefficient is -1. And the denominator of the coefficient is just the power squared, 2 factorial, times x minus 1 squared. Plus, now we're on the cubed, or the third derivative line. The numerator of the coefficient is 2. And what's the denominator? 3 factorial, times x minus 1 cubed. Plus -6 over 4 factorial, times x minus 1 to the fourth, plus 24 over 5 factorial, times x minus 1 to the fifth, and then finally minus 120 over 6 factorial times x minus 1 to the sixth. So notice again, for Taylor polynomials, you will lose a check if you don't use the squiggle. Now, for natural log, unfortunately, there's no way I'm going to be able to add infinitely many terms and ever let it equal natural log of x purely. Why? Because unlike sine of x, whose domain was all real numbers, the natural log of x only lives to the right of 0. So I can only use this polynomial to the right of 0. The polynomial is going to have a domain of all real numbers. So sometimes, if you add infinitely many terms, you don't get the exact function. And we'll talk about that in the next section. That's where the interval of convergence comes in. All right, so now that we have that, let's do this one last thing. Before we evaluate it at 1.1, let's see if we can simplify it. Because remember, the Taylor pattern can be used for any function, but every function then can have its own inherent pattern. X minus 1 squared over 2 factorial. Plus, what's 2 divided by 3 factorial? 2 factorial is just 2. 2 divided by 3 factorial, well, 3 factorial is 3 times 2, right? And the 2's divide out, so we're just left with 3. So it's x minus 1 cubed over 3 minus, well, what's 6 divided by 4 factorial? That's 4 times 3 times 2, which is 4 times 6. The 6's divide out. So we're just left with x minus 1 to the fourth over 4. Plus, guess what's going to happen here? 24 is the same as 4 factorial. So 5 factorial is the same as 5 times 4 factorial. We're just going to be left with x minus 1 to the fifth over 5. And the last term, now we can already see the new pattern. It's going to be minus x minus 1 to the sixth over 6. So if we needed to generate another term now, it would be what? The next term would be plus x minus 1 to the seventh over 7. Wow. So we could generate terms by finding the new inherent pattern in the function. All right, after lunch, we'll actually plug in the 1.1, and we'll get the approximation. Have a fantastic lunch.